Energy stored in the electric field too. So this is our second example. An isolated conducting sphere whose radius is capital R carries a charge Q. Part A, how much energy is stored in the electric field of this charged conductor? Part B, what is the energy density at the surface? Now, the energy stored in a capacitor, remember, is 1 over 2 Q squared, the charge stored, squared divided by capacitance. So the question boils down to what is the capacitance of this spherical charged conductor? Now the potential delta V of the surface charge with respect to another conductor at infinity is kq over r, kq over capital R, and remember that we take the potential at infinity to be zero. Therefore, when we talk about the potential difference, that's with respect to infinity. So we're considering a charge at another conductor at infinity. So the potential with respect to the other conductor at infinity is kq over r. Now, the charge stored is basically K divided by radius R. Q is the capacitance C multiplied by delta V, the potential difference between the plates of the capacitor. Therefore, these delta V's will cancel, and we will see that the capacitance of this single charged conductor with respect to another conductor at infinity is R, the radius, divided by K, Coulomb's constant. So this is equal to 4 pi epsilon 0 R. K is 1 over 4 pi epsilon 0. So with this capacitance, we can calculate the energy stored to be 1 over 2 Q squared divided by 4 pi epsilon 0 capital R. So if we calculate this, we obtain the final answer, Q squared divided by 8 pi epsilon 0 permittivity of free space times the radius R. So this is our answer to part A. Part B is asking us the energy density at the surface. Now the energy density at radial distance of capital R from the surface, this is equal to 1 over 2 epsilon 0 permittivity of free space times electric field squared. And what is the electric field at the surface? It's 1 over 2 epsilon 0 kq over r squared squared. So this will be E squared, and therefore we can find the energy density at the surface to be Q squared divided by 32 pi squared epsilon 0 capital R to the fourth power. Now you can see that K is 1 over 4 pi epsilon 0. So 4 squared gives us 16 multiplied with 2, 32. Pi, 1 over pi squared. And then we have epsilon 0 squared. But this epsilon 0 will make this epsilon 0 get rid of the square here. So there will be an epsilon 0 at the bottom. And r square will give us r to the fourth power. So the energy density at the surface is Q squared over 32 pi squared epsilon 0 r to the fourth power. So we're considering a single isolated conducting sphere, radius capital R, carrying a charge Q. This is a problem we have considered before. We found the potential at the surface is kq over r, capital R, with respect to another conductor at infinity. Therefore, since the charge stored is equal to capacitance times the potential difference between the two conductors, we find the capacitance to be 4 pi epsilon 0 r. If we substitute that here, we obtain 8 pi epsilon 0 r at the bottom and q square on top. That's the energy stored in the electric field. And what is the energy density at the surface? Energy density, remember, is 1/2 epsilon 0 e squared. So I need to evaluate the electric field at the surface, which is kq over r squared. So if I take the square of this and multiply it by 1/2 epsilon 0, I get my final answer.